In this video, we're going to go over the concept of improper integrals, and we're going to use the fundamental theorem of calculus to compute these kinds of integrals. Alright, this is all part of section 7.3, and we're just going to go over two examples in this video. Actually, one of them is from the book and inside the problem section. And first, let's go over why we call these integrals improper. Okay, in the first one, so I'll just circle this in yellow, so the yellow integral, we call this an improper integral because one of the endpoints is infinity. Alright, we could have made the left endpoint minus infinity and the right endpoint 1, for example, or negative 1. That would have worked too, but in this particular example, this is improper because one of the endpoints is infinity. While in the purple one, right here, the one on the right, we call this integral improper. Well, this time the endpoints are actually numbers, but what you'll notice is that you can't actually plug one of them in. Okay, you can't plug in x equals 0 into 1 over square root of x. Of course, in that case, you'd get 1 over square root of 0, which is undefined. So that's the other reason why we call this integral improper, because one of the endpoints you can't plug them into the function you're integrating. Okay, so these are improper integrals, but the idea is we can still use the fundamental theorem of calculus to get something reasonable from them at the end of the day. So let's start with this first one here, the one on the yellow one. Look how we're going to compute this. We're going to compute this just as we normally would, so I'll write it as 1 to infinity. Alright, we're going to want to use the power rule, so first let's express it as x to the minus 2 power dx. And what will we get? We'll get x to the minus 2 plus 1, that's the power rule, but then we divide by minus 2 plus 1. And of course, by the fundamental theorem of calculus, we'll evaluate that from 1 to infinity. Look what we're going to do here, though. We're not going to plug in infinity because that's not a number. We're not allowed to plug that in. And instead, we'll replace it with the number n. Alright, n is just something you'll think of as a really big number. That's why I made it capital. But now we could use the fundamental theorem of calculus to do that, because we're just going to plug in numbers now. N to the minus 1 power divided by minus 1, and then minus 1 to the minus 1 power divided by minus 1. That, of course, is just going to be, I'll write it in yellow now, negative 1 over n plus 1. Right? Okay, but n wasn't there originally. It was infinity. So how are we going to turn n into infinity? Really simple. You're just going to make n as big as you possibly can. So what happens to 1 over n when you make n really, really big? So think about it, 1 over 10, 1 over 100, 1 over 1,000, 1,000,000, 10 million. What's happening to that number? It's getting smaller and smaller, in fact, getting closer and closer to 0. So by the time n reaches infinity, you'll have 0 exactly. So this actually equals 0 plus 1, so just to note, this turns into 0, and you just get 1. And there you have it. Alright, that's what the improper integral would equal. It just equals 1. And again, the only trick is that we turned infinity into a number n, but then we later let n get as big as we possibly could. Okay, so that's the trick there. For the purple integral, the trick is actually, there won't be any trick involved. You'll see it'll just go through exactly the way we normally do integrals. It's as if you won't see the issue at all. The issue really is just an apparent one. And let's go ahead and do this. 1 over square root of x, let's turn that into x to the minus a half. So now I'm just going to use power rule. This is equal to, well, by the power rule, as I said, you'll have x to the minus a half plus 1 divided by minus a half plus 1. And I'll evaluate that from 0 to 1. Okay? Now look here. this is equal to, I'm just going to simplify the exponents there. Minus a half plus 1 is just, of course, positive a half, and then divided by positive a half. Still evaluating it at 0 and 1. And now I want you to look at the difference here. Here, when we just had before we integrated it, we weren't allowed to plug in 0, right? Because 1 over square root of x, you're not allowed to plug in 0 into that function because x is in the denominator by itself. But now after you integrate right here, so this is before, this is after. Now you can plug in 0 because x to the 1/2 is in the numerator. So after you integrate it, then you could plug it in, and that's why it's going to be okay. So here we go. We have x equals 1 to the 1/2 power over 1/2 minus 0 to the 1/2 power over 1/2. That, of course, is equal to, well, what's the reciprocal of 1/2? It's just 2. So actually, let me write that in purple. 2. Okay, there you go. So you see, we got a number at the end of the day. And really, there is no trick for computing the purple integral. We just did the same exact steps. The only funny thing that happened is that before we integrated, we couldn't plug in 0, but after we integrated, we could. Okay? So that's how you can compute improper integrals. In these particular examples, the way I chose them, they actually worked out and you got numbers at the end of the day. But watch this. I'm just going to do something really simple to change everything. That'll change your answers completely. Okay? So let's look at this instead. So if you look at this yellow integral, instead let's look at, so let me make sort of a new example really quickly. Let's instead look at the integral, and look what I'll do here, from 0 to 1 of 1 over x squared dx, while on the other hand, I'll make the integral from 1 to infinity of 1 over square root of x dx. So all I did was switch the bounds on each of those integrals, right? Now remember, this is just going to be x to the minus 1 divided by minus 1. That's what it was before. And we'll evaluate it at 0 and 1. Look what we'll get. We'll get 1 to the minus 1 over minus 1 minus 0 to the minus 1 over minus 1. But look at that. Bam. 0 to the minus 1 is equal to 1 over 0, so that doesn't make any sense. This is actually undefined. Okay? And similarly, if you look at 1 over square root of x, now we're going to integrate it from 1 to infinity, so it's still an improper integral, but look what happens. 1 over square root of x, the antiderivative of that is x to the 1/2 over 1/2. If we evaluate that from 1 to infinity, we'll do the same trick as before. All right. Instead, we'll put in n there, and we'll get n to the 1/2 over 1/2 minus 1 to the 1/2 over 1/2. Of course, that's just going to be 2 times square root of n minus 2. But remember, n needs to get really, really big because we replaced infinity with n. So as n gets really, really big, what happens to 2 times square root of n? Well, that also gets really big. So that also goes to positive infinity, which is undefined in a way. Okay? So improper integrals, the point I want to make is that improper integrals don't always exist. You might get undefined quantities as your answers. So that's what you always have to be careful of when you compute these improper integrals, but at least you know how to compute them. When you're dealing with endpoints that have infinity, you replace the infinities with big numbers n, and then you let n get bigger after you integrate. While on the other hand, you don't really have to do much, but you will notice that before you integrate, you can't plug in. After you integrate, you can. Okay, And that's all.